Welcome to the deep dive. Today we're taking a shortcut to understanding a really cutting-edge breakthrough in how large language models, or LLMs, can essentially teach themselves to reason better.
Right.
Now, we've all been pretty impressed by LLMs solving complex math problems or, writing functional code. They show this incredible precision.
They absolutely do. And that precision, well, it usually comes from a training method called reinforcement learning with verifiable rewards, or RLVR.
Or LVR, right.
It's incredibly effective because for tasks like math or programming, you have a clear objective signal. The answer is either right or the code runs without errors.
Yeah, it's black and white.
Exactly. That clear feedback loop makes it, well, relatively straightforward for an LLM to learn and check its own work.
But here's the core challenge, and it's a big one. That clear right or wrong signal just doesn't exist for a huge category of real-world tasks we call open-ended. Think about revising a complex legal document, writing an analytical summary of a sprawling report, or reviewing intricate financial statements.
Yeah, there's no single universally agreed upon correct answer there. It's far more about nuanced reasoning, human preferences, and the quality of the thought process itself.
Precisely. And that's where traditional methods really hit their limits. You can't simply apply RLVR.
Right. For example, using another LLM to act as a judge. Well, it might sound appealing, but it introduces a whole host of issues.
Like what?
Well, it can be overly sensitive to how you phrase prompts. For one, it might fall victim to reward hacking.
Where it games the system.
Exactly, where the model learns to exploit the judge's weaknesses rather than truly improving its reasoning. And it creates this generator-discriminator gap between the model being trained and the one doing the judging.
Okay, so if another LLM can't reliably judge, what about just using something simpler, like similarity metrics, Arrow scores or cosine similarity?
Yeah, people try that, but they might tell you how much text overlaps, but they completely miss the point, don't they?
They seem like they would.
They can't assess the quality of the underlying logic or the coherence of the actual reasoning. They prioritize superficial lexical similarity over true logical or structural alignment.
So they just don't capture what makes good reasoning good.
Exactly. Not for these open-ended tasks.
This brings us to our mission for this deep dive.
Yeah.
The research we're exploring introduces a brilliant new framework called Direct Reasoning Optimization, or DRO.
DRO, yeah.
Which uses an ingenious new reward signal called Reasoning Reflection Reward, or R3.
R3, got it.
The core idea: it lets LLMs literally teach themselves how to reason better, even on these notoriously tricky open-ended tasks, all without external human feedback.
Which is the really exciting part.
Okay, let's unpack this.
So when an LLM tackles a complex problem, it often generates a chain of thought, or code.
Right, the step-by-step thinking.
Exactly. It's reasoning process before it produces a final answer. You can think of it as an implicit intermediate state. It's like watching the model think aloud, working through the problem behind the scenes. Now, what's fascinating here is that intuitively one might think, okay, maybe we can reward good reasoning by simply looking at how certain the LLM is about its final answer given its COT.
Right. If the thinking is good, the answer should feel confident to the model.
Yeah, exactly. That's called self-certainty. That sounds logical, right?
It does seem logical on the surface.
But here's where it gets really interesting. This intuitive self-certainty approach actually, well, it falls flat for open-ended tasks.
Why?
The research points to two big hurdles it just can't overcome. The first is what they call reasoning token blindness.
Reasoning token blindness.
Okay. Imagine a long piece of text, like a revised paragraph. Most of the individual words or tokens in that text end up having very similar log probability values from the LLM.
Log probability being its confidence in that word.
Yeah, essentially how confident the model is that it should generate that specific word next. And the problem is, these values are often similar regardless of how good the preceding chain of thought was. Only a very small subset of tokens truly reflect the influence of the reasoning. These are the reasoning reflective tokens.
So to bring that to life, the source gives a perfect example, right?
Yeah.
From a paragraph revision task.
Exactly. Imagine an LLM trying to revise a paragraph about scientific paper sections. One reasoning path, let's call it reasoning A, correctly identifies that section 4 needs to come before sections 2 and 3.
Okay, a structural change based on reasoning.
Right, and makes that adjustment. Another path, reasoning B, basically just gives up or says, I can't improve this.
Okay.
Now, if you then just average the model's certainty over all the tokens in the final revised paragraph,
You lose the important bits.
precisely, The poor reasoning path, B, might actually look better than the good one, A. Maybe just because reasoning A had a single crucial low certainty token, like in the number 2 when it was reordering.
Wow, so the few critical tokens that truly show the reasoning's effect get completely drowned out.
Exactly. Drowned out in the noise of all the other, less informative tokens. That's token blindness.
Okay, what's the second hurdle?
The second hurdle is called reference tokens compensating for poor reasoning.
Okay.
This is about how LLMs generate text token by token, right? Each new token is conditioned on all the previous ones.
Right, autoregressive.
Correct. So this means that if the LLM makes an initial error in its chain of thought, but then the reference answer itself provides the correct sequence of tokens.
The model gets bailed out by the answer it's trying to predict.
Kind of. Its certainty for later tokens can artificially inflate. It essentially masks the earlier flawed reasoning.
It's like the Lionel Messi example from the source.
Exactly that example. If the model's chain of thought doesn't correctly identify the goal scorer, its probability for the token Lionel might be low.
Okay.
But once Lionel is generated, maybe because it's in the reference, the probability of Messi suddenly becomes very high, just due to that incredibly strong word association.
But the high certainty for Messi doesn't actually reflect good reasoning.
Not at all. It just reflects that strong word association, masking the initial poor reasoning.
So it highlights a fundamental challenge in how these models work that can easily mislead standard reward signals.
Precisely. And that's why these two issues, token blindness and reference compensation, make simple self-certainty a problematic signal for open-ended tasks. It's just too easily misled.
So how do they fix these deep-seated issues? This must be where the reasoning reflection reward R3 comes in.
Bingo. R3 is the core innovation here. It's designed to be token-level dense, meaning it looks closely at individual tokens, and it directly tackles those two hurdles we just discussed.
Okay. How does it tackle token blindness?
So instead of treating all tokens uniformly, R3 identifies and emphasizes those crucial reasoning reflective tokens.
The ones that actually matter for the reasoning.
Exactly. How? It looks for tokens whose likelihoods show high variation when conditioned on different chain of thought traces.
High variation meaning their probability changes a lot depending on the reasoning path.
Yes. Think of it like spotting the controversial words, the ones that change their probability drastically depending on how the model reasoned to get there. R3 statistically finds those high standard deviation tokens, and then it weights these high variation tokens more heavily in the reward calculation, amplifying their influence.
So those crucial words, like gives or existing in that paragraph revision example, which actually show the model understood the restructuring, they finally get the attention they deserve. It's not just averaging everything out anymore.
No, it's a much smarter weighting. And to mitigate the compensation problem.
Right. How does it stop the reference tokens from misleading the reward?
It uses a really clever technique. One effective way, the more efficient one they mention, is by calculating two log probabilities for the target tokens.
Okay.
One using the actual chain of thought generated by the model, and another using a masked or sort of baseline chain of thought.
Masked COTI, like a generic one.
Sort of, yeah. A baseline that doesn't contain the specific reasoning. Then, by subtracting the log probability derived from the masked 2t.
You isolate the difference.
Exactly. R3 isolates the true certainty boost that comes specifically from the model's own reasoning, not just from the strong lexical association within the reference answer itself.
That's a really clever approach. It strips away the easy wins from word association and forces the model to focus on the actual contribution of its reasoning.
It's a fundamental shift, making the model learn what genuine causal reasoning looks like for that output.
Okay, so that's R3. Now let's look at the full picture. Direct Reasoning Optimization, or DRO, is the complete fine-tuning framework that puts R3 to work.
Right, DRO is the whole package.
And it actually builds on a widely adopted reinforcement learning technique called Group Relative Policy Optimization, or GRPO.
Yes, GRPO, which is designed inherently to compare multiple reasoning attempts, multiple policy samples.
Which aligns perfectly with how R3 works, comparing different cuddles.
Exactly, it's a natural fit. So behind the scenes, the model generates multiple chain of thought traces for a given prompt.
Several different ways of thinking about the problem.
Right. R3 is then computed for each of these COTI traces, essentially scoring how well that specific reasoning path aligns with the correct reference outcome, using that smart token weighting and baseline subtraction we talked about.
And here's the really clever part. You mentioned this earlier. The model computes this R3 score itself.
Yes, that's huge. It eliminates the need for an external reward model or any human feedback loop during this fine-tuning stage.
So the LLM becomes its own incredibly discerning teacher. It's constantly refining its inner thought process based on its own assessment using R3.
Fully self-contained, which is much more scalable and efficient.
They also mentioned something about length.
Yes. Additionally, DRO incorporates a small length penalty on the final outcome.
Why is that?
Just to prevent the model from becoming overly verbose,
Yeah.
To encourage it to produce concise and efficient revisions or answers, which is often what you want in practice.
Makes sense. Keep it focused. Okay, beyond the core DRO and R3, what about efficiency? Training these models is expensive.
Right. And the researchers highlight the critical role of data filtering, especially because for these open-ended tasks, filtering data effectively is hard. There's no simple, correct signal to filter by.
So how does DRO handle that?
It introduces a generic, dynamic filtering mechanism that cleverly leverages R3 itself. This is another key innovation.
Using the reward signal to filter the training data. How?
It's a two-stage process. First, it filters out questions that are beyond knowledge or just too difficult for the model at its current stage.
How does it know if it's too hard?
The model samples multiple critique traces for a question and checks its prediction difficulty over the reference answer. They use something called token rank, basically. How far down the list of possibilities the correct token was.
Okay.
If the model is extremely uncertain, like the correct token is consistently ranked very low across all its reasoning indents, the question is deemed too hard for now and filtered out for that training round.
Smart. Don't waste time on impossible problems. What's the second stage?
The second stage filters out questions with low reasoning variation. If questions are too simple, they don't really help much with improving reasoning.
Right. Low-hanging fruit isn't useful for advanced training.
Exactly. DRO identifies these by looking for questions where those crucial reasoning reflective tokens show very low variation across the different QWERTY traces.
Meaning the reasoning path didn't really change the outcome much for those key tokens?
Precisely. It means the reasoning isn't making much difference, maybe because the answer is obvious regardless of the QWERTY, so these simpler questions are also filtered out.
So this R3-based filtering, it sounds like it really focuses the training.
It has a dual impact. It not only improves downstream performance by focusing training on the most informative examples for reasoning improvement, but it also reduces training cost and time significantly.
Getting better results faster and cheaper.
That's the goal. It's like finding the optimal learning curve, ensuring the model spends its energy on the lessons that provide the most value for enhancing its reasoning capabilities.
Okay, the theory sounds great. But the real test, of course, is in the data. What did the experiments actually show?
They're pretty compelling, especially for those really tricky open-ended tasks. They used a data set called ParaRev.
Paragraph revision.
Yeah, revising paragraphs in scientific papers based on reviewer comments. A very human-centric, nuanced task, right?
Definitely open-ended.
So on ParaRev, DRO, using this R3 reward, achieved significantly higher win rates against GPT-4o.
Against GPT-4o. Wow, that's a very strong baseline.
Much larger and incredibly capable model, yeah. DRO-R3 outperformed the base model by 8–10% in win rate, and get this, even surpassed GPT-4 itself in human preference evaluations.
So humans preferred the DRR3 revisions even over GPT-4os.
That's what the evaluation showed. It indicates a much better alignment with how humans actually prefer revisions to be made, which is huge for this kind of task.
And compared to those simple RG score rewards.
Oh, massive difference. As we suspected, RG-based rewards often led models to just leave paragraphs unchanged to maximize that superficial text overlap. R3 showed a 16–20% higher win rate compared to that.
So it really stopped the models from just gaming the similarity metric.
Absolutely, and it also significantly outperformed methods that just use that basic aggregate certainty we discussed earlier.
So it really proves the importance of R3's specific token weighting and baseline comparison.
Definitely. This isn't just a marginal improvement. It seems to fundamentally change how these models approach open-ended revision tasks.
Now, for the training insights, you mentioned some aha moments.
Yeah, this is really interesting. Optimizing for reasoning quality with R3 actually encouraged the model to produce longer, more elaborate chain of thoughts.
Longer? How much longer?
They grew significantly, from around 1,000 tokens on average up to 2,500 tokens.
Wow. That really suggests the model was engaging in deeper, more complex reasoning, right?
That's the interpretation. In stark contrast, those aggregate certainty rewards led to the reasoning process kind of collapsing into very short, shallow outputs.
Fascinating.
And what's truly astonishing is that by focusing purely on reasoning quality via R3, the model also implicitly improved its textual similarity. The Rouge-L F1 score went from about zero point 0.4 up to 0.7.
Even though Rouge wasn't the target.
Even though Rouge wasn't part of the reward signal at all, it's almost as if understanding the logic naturally leads to better, more aligned writing.
That makes intuitive sense, actually. And the filtering.
Ah, yes, the dynamic data filtering using R3. It reduced training time by a substantial 45%.
45%, that's huge.
Massive savings. And it achieved comparable performance results while also leading to smoother convergence during training. So much more efficient overall.
Okay, so R3 clearly shines on complex, open-ended tasks like PairRef. But what about more structured scenarios? Did they test its versatility?
They did. To really test its versatility, they also applied DRO to FinQA.
FinQ, financial question answering.
Right. It's a task that's more math-like, often involving calculations based on financial tables, leading to shorter, more definitive outputs, kind of closer to the right or wrong end of the spectrum.
Okay, so how did R3 do there compared to, say, just rewarding based on getting the final number right?
Amazingly well. On FinQ, R3 achieved results that were comparable to, and in some cases even outperforming, the ideal correctness-based rewards, the ones that rely on having those perfectly verifiable answers.
Performing the ideal reward. How?
Well, it shows R3 isn't just for fuzzy, subjective tasks. It seems to capture something fundamental about the reasoning process, even when there is a right answer.
And even for these shorter math-like answers, R3 still beat the simple aggregate certainty approach.
Yes, it did. Which highlights that those reasoning reflective tokens aren't exclusive to long-form text.
How would that work in a number?
Well, for example, in a financial number, maybe the decimal point or a specific digit resulting from a calculation step might be more reflective of the underlying reasoning than, say, trailing zeros. R3 seems able to pick up on those nuances.
Interesting. Any training insights from FinQA?
Similar trends. R3 consistently improved the reward signal over time and led to the emergence of longer reasoning chains, even after the initial reward value seemed to plateau.
So the model kept refining its explanations even after it was getting the answer right.
It suggests that, yes, it continued to explore richer explanations, demonstrating a pretty robust and continuous learning process driven by R3.
Okay, let's bring it all together then. Direct reasoning optimization, DRO, seems like a really powerful new framework.
It does. It uses that unique reasoning reflection reward, R3, along with that smart dynamic data filtering.
Allowing LLMs to self-optimize their reasoning, especially for these complex open-ended tasks, without needing external human annotation or reward models during fine-tuning.
Exactly. And this work really highlights the immense promise of what they call self-supervised reward design.
Designing rewards from the model's own signals.
Right. It means we can potentially build more capable and more efficient LLMs. Models that can tackle nuanced real-world problems where the right answer isn't always black and white.
Moving beyond simple correctness.
Truly. And because it can make training faster and cheaper by removing the need for external models or extensive human feedback for this stage, it could make these advanced reasoning capabilities more accessible.
So here's a final thought to leave everyone with. If LLMs can now internalize what constitutes good reasoning and refine their own thought processes for these complex, open-ended problems, well, what does this imply? What does it imply for how we'll interact with and rely on AI in areas like, say, creative writing, strategic planning, complex analysis, maybe even ethical decision-making support in the near future?
That's a big question. It definitely opens up possibilities for AI playing a more significant role in tasks that require deep, nuanced understanding.
Something to definitely mull over. Thanks for unpacking that with me.
My pleasure. Really fascinating work.
Until our next deep dive.